Hello, this is Camille Fairborn from Michigan State University, and I'd like to welcome you to today's Cause Teaching and Learning webinar. I'm pleased to introduce Dr. Vicki Woodard as our speaker today. She is an assistant teaching professor in the Department of Applied and Computational Mathematics and Statistics at the University of Notre Dame. That is a mouthful. For today's webinar, she will give a presentation entitled Statistical Computing: How Does It Impact Statistical Thinking and Problem Solving? The way the webinars work is that all listeners are muted during the webinar. You can ask questions at any time by typing them into the questions box. We'll be sure to ask those questions towards the end and give Dr. Woodard a chance to respond. You can also use the chat box if you are having any technical questions. At this point, I'll turn things over to Dr. Woodard. Vicki, go ahead.
Thank you, Camille. I'm going to actually take my camera off of me so that I've got the bandwidth that I need, but I wanted you all to be able to at least briefly see who was talking to you, not just some disembodied head. So I am going to be talking about statistical computing and how it impacts statistical thinking and problem solving. And I feel like this is actually a very appropriate topic right now, given that JSE has just called for some papers for the 10th anniversary of Temple and Nolan Lang's paper that they wrote. So hopefully we can get some stuff out of this and a conversation started, and I'd love to hear your thoughts on anything that I discuss here. So a little bit of background on where this came from. I did my dissertation in 2016-2017 under Holly Lynn Lee, and this is multiple parts of what I did for that study. So it's a very broad scope of what I did, and I'm not going into the depth today because I won't have the opportunity to, but I do have my dissertation out there if anybody wants to happen to read 200 pages worth of this and get a little bit more depth. But I was sitting in class reading about guidelines from GACE, and one of the things that stuck out to me was that they cautioned against programming in R and other more advanced topics. But then we were reading about individuals that were doing these courses where they were implementing R into their introductory course, and they were successful with it. And success can mean different things to different people, but students were able to understand what was going on and do the homework assignments, and I was thinking, well, if they're able to be successful, why are we cautioning teachers against using R in these courses? And I got to thinking about it, and what I realized was students can repeat what we're doing. In fact, I would consider a student successful if they passed my course. But that doesn't necessarily mean that they are able to think statistically while using those computing tools. They might just be repeating what we're doing. And they might not be able to solve new problems while they're using those computing tools. So I wanted to dig deeper into these two questions and learn a little bit more about how students thought statistically and how they solved problems while they were using these statistical computing tools. So I promised in the abstract I'd give a little bit of methodology of how I did this study because it was qualitative. So you'll see as I answer these questions kind of the methodology that I used, and hopefully that'll give a little bit more than just us using p-values to find answers to things. It'll give us some other evidence that's not quite so p-value, yes, no. In order to do this study, I had 14 students that took a Statistics 2 course with me at an all-women's college. Of those, 6 of them had only taken introductory statistics. 5 had taken statistical computing on top of introductory statistics. 2 were computer science majors or minors. They would have had to have taken intro stats to be in the course, but they didn't necessarily have to have anything else on top of that. And then I had 1 psychology major who had stats and some SPSS experience. During the course, I had students complete writing assignments, and I ended up using these, and I'll discuss a little bit more about what they provided me. But they were assessments during the semester. A total of 91 documents were collected. They all necessitated the use of the computer to solve, and because I was doing this research, I was using R in the course, and students were required to use R in order to solve these. And then they utilized something called the 4-sentence structure, which was created by Roger Woodard, and he presented it back at JSM in 2016. I'll go a little bit more in depth into what that is in just a little bit. I also did task-based interviews. These were done after the semester was over, so students weren't in the depths of learning these things. They'd had about a month to 2 months off and wanted to see kind of what they retained. There were 5 students that volunteered for this. It was a 3-phase interview, but I really only used the first phase where the computer was necessary in order to solve the problem. So I wanted to study statistical thinking and statistical computing and see their relationship. And Wild and Fancook have this amazing statistical thinking framework out there, and they did all of the work for me. I didn't have to really do anything for this. I just needed to be able to identify these items in students' work to see the statistical thinking that they were utilizing. Several others have done research on this, so I added to that. I did a little lit review and came up with bullet points for actions that students might take. And these were the things that I looked for as I was going through student work to try and identify statistical thinking. Statistical computing, though, didn't have quite the background. The research that I found when I was doing this was more about what's taught in a statistical computing course, as opposed to actions that students might take to demonstrate statistical computing. And I found this quote from Nolan and Temple Lang in that 2010 paper, and ultimately what I felt like it boiled down to is that statistical computing is about the journey. It's not about the destination. And so I think a lot of students see the computer as this tool to get them an answer, and they're not utilizing it in all of its glory and using it for the journey that it can take them on. So when I tried to create my framework for statistical computing, the action students might take, I kind of use this as my guiding light in that. Unfortunately, there's very little, as I mentioned, about statistical computing actions students might take. It's more about the courses. So I had to go into the computing realm and see what they said were actions that students might take and things that we might look for within their work. And if you read this framework that I have here, it's actually very broad in that this could be used for StatCrunch, or it could be used for Python. It's not necessarily geared straight towards statistical computing. So I was looking for these framework aspects when students were using a statistical computing tool. I did not come up with something like Wild and Fancook that was specific to statistical computing. I didn't think that there was anything necessarily that specific. So it's a very broad framework. It could probably be used in other realms, but this is what I felt students might do as we're looking for actions they might take while using statistical computing tools. I felt like there was this symbiotic relationship between the two. It's obviously a lot more complex than what I have there on the screen, and that's what I wanted to explore as I was going through. So how are they related? In order to study this, I took those writing assignments that students created and I analyzed them. I mentioned that they followed the 4-step structure. Students were asked to write in this form specifically so that I could, one, get them to write better, and 2, it helped me with analyzing their work. I had a structure that I could use to break down what they had done. But in this structure, students answer the question, state the relevant facts from the problem, state the implications that the facts imply, and explain how the facts lead to the conclusion. And I felt like that 3rd step there was where I would really get to see students' statistical thinking. I think a lot of times students assume we know what they're talking about, or maybe they don't know what they're talking about, they're just repeating. But by having them state those implications, I was really drawing out student statistical thinking. So on the screen, I have an example of what students, or what a particular student wrote as a response to one of the questions that I gave. And what I did is I took their statement and I color-coded it for the 4-sentence structure. So in red, that first line up there is the student answering the question. In orange, that's actually an implication. And then in blue, we get our first fact. And the student didn't use any statistical thinking or statistical computing as they were making their first two statements. So on the right, you don't see anything coded for any of my constructs from my framework. But in that first blue statement that you see there, that's their fact that they've given. The student had correct context and incorrect modeling, both constructs from the statistical thinking framework. So I coded those so that I would be able to see where we had correct and incorrect statistical thinking. And you can see those on the right in green for correct and red for incorrect. Additionally, you can go down the page a little bit. You can see pattern recognition and decision making. That's one of the statistical computing constructs, and that's in blue. If they'd had any incorrect statistical computing constructs, those would have been in yellow. So I was looking at these documents. I had 91 of them. I'd coded them all up like this, and I was a little bit stuck. So I asked my advisor what to do, and she said, well, just do what any statistician would do and condense down all of the data you have to something smaller so you can look for patterns. So that's what I did. I created these document diagrams, and the one that you see at the top of the page there corresponds to the document from the previous page. So the student first answered the question, but there were no constructs in there. They then had an implications statement, but there were no constructs in there. And then finally there was a fact, and there was both correct context and incorrect modeling in there. And I ended up with 91 of these, but you can see now that I've got all 91 of them on the desk in front of me, and I was able to play around with them and come up with patterns that I was seeing between them. So again, a little bit of methodology on how you might go through and analyze some qualitative work. What did I find? The first two items that I have here are kind of broad. They aren't necessarily answering the question, but they were observations that I made. The first one is that students' work does not always provide evidence of statistical computing. The first place I noticed this was in their first assignment. Students were not used to using the computing tools, and they just decided that they were going to answer the question without it. So I had to make sure that I told them for the second assignment, use the computer. We want to see what you're doing for computing on these. But the other big place that I saw this was limitations of my framework. And the reason for that is I was looking for actions students were taking, and I was reading about what they did, but students don't always tell me what they did. So a huge limitation of this framework is that it's not great for writing assignments. You almost have to imply what students did in order to use it. And this is where the second part of the presentation comes in, where I decided to do these interviews with students so I could see the actual actions that they were taking. The second thing that I found from this, and I'm not exactly certain where this might lead, but I found it to be interesting, is that students' arguments that they created only had statistical computing in the facts, never in the implications. And I know I wouldn't have found this without the four-sentence structure, and what I think it might mean is that students rely on the computer to present facts, but it doesn't seem to be anything beyond that to them. So that would be something interesting, I think, for people to study and see how students are using the technology. The remaining three items were the relationships that I saw occurring between statistical computing and statistical thinking based on these writing assignments. In about a third of those 91 documents, I saw where students had purely good statistical computing and good statistical thinking. And what I found was that good statistical computing was informed by, worked in conjunction with, and led to good statistical thinking. So it was highly intertwined. The two of them together come together quite often. I also saw good statistical computing, but it was paired with pitfalls in students' work that led to poor statistical thinking. And some ideas behind that would be that students were relying heavily on the computer to produce a solution. They were too trusting of the output that they saw. Maybe they didn't do any EDA, they just jumped straight to inference, and they weren't looking deeper into things. They were manipulating interpretations to confirm prior suspicions. I mentioned that this was an all-women's college. I gave them a problem where they were trying to predict ideal mate height from their height. And since they're female, they all knew they wanted somebody taller than them. And they found output that they thought supported the suspicion. However, they were misinterpreting what they found and jumping to conclusions prior to when they should have. And then additionally, just having poor statistical knowledge for interpreting computer output. I had students confusing R squared and AIC criteria to pick the best model. And then finally, a lack of statistical thinking prior to problem solving was leading to poor statistical computing. In particular, students were coming up with poor solution strategies, and they were coming up with these new methods that were just completely incorrect, and they showed no prior thinking about what to do for the problem. So because they weren't thinking about it, they jumped right into the technology and were doing incorrect things. So the implications of this, I think students should have a good basis for both statistical thinking and statistical computing to solve problems. As teachers, we need to know potential pitfalls that can lead to incorrect solutions. Oops, sorry about that. Here we go. By knowing where students might fail, that can help us to prevent that from happening in the future. Of course, that comes with experience. And then finally, we should encourage our students to think statistically about a problem before they attempt any statistical computing tools. And I think that goes against what we know about with EDA. We tell students, oh, go ahead and jump into the data and explore what's going on. But I think EDA is the statistical thinking in that regard. So that's really what I mean by that, instead of just jumping in and trying to do inference with the tools that they're given. All right, so next is problem solving. And this came from the task-based interviews that I did. Again, they were completed about a month or two after the course was over. And students were trying to solve an ANOVA problem with data that was not in a standard form. So normally I would give them data where the X and Y variables would be in their own columns. In this particular problem, I gave them data where they had the first explanatory variable level, and then the data was underneath that. And then the second level, and the data was underneath that. And then the third level, and the data was underneath that. So before they could even do ANOVA, they needed to go through and concatenate these variables together to create one long explanatory variable, that would give the responses, and then create the explanatory variable from scratch. What was neat about this is I was getting to see how students worked through problems in a similar setting to their homework. So I had a video camera on them so I could see their face. I was screen capturing what they were doing, but I told them they could go on the internet, they could research anything they want. Their goal was to solve this problem. Similar to the 4-sentence structure from up above, I needed some sort of way for me to be able to assess what was going on and segment their work. So I used Lee and Hollobrand's problem-solving structure. What I ended up finding from this was, because I was allowing students to go on the internet, I needed to add research as a separate category. I had originally been putting this under planning. However, I found that planning was getting just oversaturated with things, and there was really this dichotomous nature of things in there. So I ended up recoding things where students had gone on the internet from planning to research. To give a little bit of background, and I think this is important to understand the students' background to figure out what's going on here. I had these 5 students. Allison was a senior. She had done lots with stats and computing. She was by far the highest ranked statistical and computational. And then from there, it's actually kind of subjective. I didn't have any sort of method to rank these, but I had them all in class. I gave them a demographic survey. I had seen them working on projects and things like that. So being a small class as it was, I knew these students pretty well, and I feel pretty confident in these ranks that I've given them. One thing to note, Moira, my computer science major, she was ranked 2nd computationally, only because she was a sophomore compared to Allison as a senior who had taken lots of computing courses. But she had very little experience statistically. All right, these graphs have so much information in them. I'm going to try to leave it up as long as I can so you can soak it in. But I'm going to give you a couple highlights from this that'll help me discuss what's going on in my findings overall. So Allison took the shortest amount of time to do the interview, and Moira took the longest amount of time. However, both of them were able to solve the problem. So time was not necessarily an indicator of their ability to solve. Cora was the only other one that was able to solve. Both Genevieve and Samantha ended up struggling so much that they only came to a solution because I basically told them how to do it in the end. They were both going to give up otherwise. Cora and Moira have a lot of color change throughout their problem-solving phases. So they were changing phases quickly and often, whereas Genevieve and Samantha have these very large blocks of research. So those are kind of the highlights of things that I'd like to look at on there, which will help me discuss on the next slide, 2 slides. Additionally, I went through and looked at the proportion of time that students spent in those different areas, and overlaid on this, those letters are the types of statistical computing that were utilized at some point during those phases. You can see that Allison and Moira spent very little time researching. Allison was the only one that had automation of computational procedures. That was the A. And then we have Genevieve and Samantha, who spend an awful lot of time under research. So what this told me was there was a hierarchy of problem solving when using statistical computing software. I felt like the best student, or student in this case, Allison, was able to use the software to automate computational procedures. She came up with a solution strategy. She was able to tell the computer what to do. She got an answer, problem solved. She had a little bit of fuzziness. It had been a month since she dug into this, but for the most part, she felt very confident in what she was doing. The next tier down, this would be for Cora and Moira, 2 that were able to solve, but not necessarily as quickly. They both had the problem-solving strategy of research, plan, implement, assess. And those were the 2 that had that rapid succession of change. They thought of something they might want to do. They looked up how to do it on the internet. They tried it, didn't work, go back and repeat. But at least they weren't afraid to try, and they did eventually end up getting to a solution. And then finally, the lowest tiers where students spent a lot of time researching how to do the problem, as if they're afraid to try anything, and they don't really move forward on the problem. I found that students that had strong statistical and computational backgrounds, and by students I mean 1, this is a small qualitative study. This is very generalized, not very, it's not very big group of people to look at. So this is kind of generalizing broadly. Those with strong statistical and computational backgrounds use the computer to automate computational procedures. They say once you have 1,000 hours programming that you become an expert in it. So Allison had a lot of time to practice with the tools. She's becoming more comfortable with them. That is where she's getting into her higher tier on this problem-solving ladder. Students with the moderate to strong statistical or computational background seem to have a problem-solving strategy, and we're able to use that to program. So Cora was stronger statistically and Moira was stronger computationally, but both of them had some confidence, I feel, and were not afraid to try something to work towards a solution. Whereas those with weak statistical and computational backgrounds, they end up being frustrated and they spend a lot more time researching than working forward on a solution. The implications of this: course technology should be chosen carefully so that we can work towards the goals of the course. And think about the students that are taking the course when you pick that. So I didn't need to use R in this course. I could have used some other technology, but I wanted to do it for the research purposes. It probably would have been better for some of the students if I hadn't used R. If you are going to use it, identify students that have the weak statistical and computational backgrounds and help them develop this problem-solving strategy. Make them feel comfortable just doing this guess and check to work towards something. You can't stare at it and let it get a solution. You have to try something. And then finally, teachers should not become a crutch for their students. And I learned this during the interview. When I was working with Genevieve, she asked me so many questions during the interview, and she kept getting so frustrated with me that I wouldn't answer. And I finally asked her, well, what would you have done during the semester? Her response was, I would have come to you. And it made me realize that there are students that don't know what they're doing, and their first instinct, especially in today's world of technologies, you can get an answer instantly. Let's just do that. And I had become a crutch for her. So just be mindful not to be a crutch for your students. Some references for you, and if you have questions, I would be happy to answer them now. Thank you very much.
Well, and thank you, Vicki. I have a couple of questions, and then of course, if any of you have some questions that you want to ask Vicki at this point, go ahead and type them into the questions menu or the questions box. The first question was, are you referring statistical computing as a software course? Are you thinking of statistical computing as a software course? I guess that means.
Yeah, so when I talked about statistical computing here, what I'm thinking about is utilizing statistical computing tools, not necessarily a course on statistical computing.
Okay, so just their skills in being able to play with data in the computer format.
That's correct.
Next one says, you made a statement that EDA is the statistical thinking in that case. Do you have any evidence that shows that students actually think statistically as they perform EDA rather than just mimic what was done before? And at what stage in student maturity do they get this skill?
I don't know necessarily what stage they get that, but for example, Allison during the interviews, she created box plots of the data that she had, saw that there was a difference in the widths and locations of the box plots, and thought that from that there would be a difference in the response for the different categories. And while I discussed what ANOVA was and why we did it, I don't recall necessarily saying words like that to her, and she described it in such a way that she was thinking statistically about what was going on, and used that as a diving board into why we would need to do ANOVA.
Okay. A next one, what about good statistical thinking but poor statistical computing? Did you see any of this?
In the documents that I saw, there were some that had that, but there weren't necessarily those led to. So let me go back to this slide here. I kind of gleaned over this. I didn't actually talk about this. There's these little, I didn't name it causes. That's what the software did. But there's these links that I've got here. So it says here, this causes 29-4. So I was looking for these connections that I found when I was working through. So not necessarily, but again, I only had 91 documents. There very well could be.
Okay, so I guess my follow-up to that is, you're saying then that students who are statistically strong but not did you have any students who that felt were statistically strong but really struggled computationally with the computer?
I felt like Genevieve, even though she was, let me get my numbers here. Genevieve, who was ranked 3rd statistically, but ranked 4th computationally, I felt like she was fairly strong statistically. She had the psychology stats background. They had them take at least 2 stats before she came to me. So I felt like she had the background statistically, but because she was struggling so much with the computational aspect of things, she almost gave up. I mean, she did give up in the interview, but in class she struggled a lot.
Okay. Next one says, on one slide, according to my notes, you said something like good statistical computing can lead to good statistical thinking. Can you discuss some strategies for helping students do this?
That is a great question. I would probably need a little bit more time to think about that. Okay. Yeah, I don't think I have an answer for that off the top of my head, but that is a really good question to look into.
Well, I will encourage that questioner to contact you outside of the webinar framework then.
Sure.
Next one says, I use 2 different softwares in 2 different courses, both introductory. In one course I use R and in the other I use StatCrunch. Can you suggest how to know which software should be used when? Do you have any experience in that?
So I am a proponent of not using R for any student that is not going further in stats. So I wouldn't use R in my intro stat class here at Notre Dame, even though they are fantastic students and I think they might be able to handle it. I don't think it's a necessary thing, and given how much it can discourage students, I wouldn't want to do that. I love StatCrunch. I used StatCrunch in my courses before for intro stats before I came to Notre Dame, and found it to just be amazing, and students found it so intuitive. I use R with my majors once we get to Stat 2 here, and I did it at this all-women's college as well. I can't speak directly to you because I don't know the level of your students, but I think you could probably ask them, does this frustrate you? And use that information to guide if you're going to use R again. Even if some students say this was the best thing ever, I'm going to use this for everything, I worry about leaving students behind, especially students like Genevieve, who she had such a passion for it. She did not need to take this class, and then all of a sudden she was just frustrated beyond belief, and I hope I didn't turn her off to stats in the future.
Okay. Another one, the students that spent a lot of time researching but didn't make progress, did you find that they might research something that would make progress to a solution, but they didn't have the requisite knowledge to know what they researched would actually lead to progress, so they didn't use it? Does that make sense?
Yes, it did. So there were times they would research and find something and it was the exact solution they needed. I was sitting on the edge of my seat waiting for them to just put it in the computer, and they just glossed right over it and went on to the next thing. And then there were other times that they would look at something and they would try it, but it would be incorrect and it wouldn't work, and then they'd get frustrated. So both things happened there. And I don't know how to teach students how to look at a website and determine if the information is good and they should use it, or if they should just pass it right over. I think that just comes with experience. And there's so many websites out there now that you could just say how to do ANOVA in R, and they'll come up and they'll show you, but that doesn't mean that they're helpful. And new ones pop up every day that might be, and I don't know how to keep up with it to help my students.
Right. So then, based on your experience with this research, what are your thoughts on using a graphical user interface that generates code for students to make it easier for them to use the statistical software program and easier to learn how to program?
I think that that is a great idea. I really do. I would love it if all of my students knew how to code before they came in. But if they don't, then if you use a GUI that produces the code and shows it to them, then They can utilize it if they want. They don't have to. And I mean, that would be very helpful to the dichotomous nature that I saw in my class of some students being so far ahead of the others. I think that's a good idea.
Okay, I'm trying to glean out from here. How does using software help students taking second statistics course learn statistics methods? So I guess that is, do you feel like the software really helped them learn the methods in the course that you taught, or?
If I'm understanding the intent of the question, it's, if you hadn't been doing research, why would you use this anyway? And I would use it for students who are planning on going further in stats and we're going to be utilizing this later. I would not have relied as heavily on it in the course. I would not have made as many assignments based on the technology. It would have been more about an introduction to it, getting them used to it, but it would not have been a tool to help them build their statistical thinking knowledge base. I really like the way that I get to do it here at Notre Dame because I now have a course and I have a lab. And in the course, I focus on the statistical thinking pieces of it. And then in the lab, they are working on the computing aspects of it. So since it's so separate, and yes, they're working on the same topics in both places, but it separates them physically and mentally into the two realms. And I think that's helpful when you're learning these at the beginning. It's not till later that we should merge them and start working as implementing them and integrating them in that that diagram that I had, how solidified they are together, in this thing right here. So I don't remember what the original question was. I think maybe I answered it, hopefully.
So you would propose, just so I understand what you're saying, you think that in an intro class, having the statistical part, this thinking part separate from the computing part is beneficial, and that it's only later on that students can start integrating them together. Is that?
Yes, yes.
Okay. Okay.
In fact, I really liked Moira's interview because she talked a lot about this is how I would have done this in SQL, or this is how I would have done this in Java. So she was actually able to come up with a solution strategy in a different language. And it wasn't as if she had learned them together, but she was still able to then start making these connections between them. So if I had my way, for any student that we were planning on using R in their education, I would make them learn a programming language before they came to my class. I don't care what it is, just something so they get that logic base and they feel comfortable programming. And then if you want to implement the R at the same time, it's okay. But yeah, as you said, learning them in these separate scenarios and then trying to pull them together, I think that is a better way to do this.
Okay. I guess this is one more, and this one comes with a disclaimer, with an apology for it being a potentially difficult question.
Okay.
When you said some of the better interview students changed statuses more often than the weaker students, that had me thinking that they had better metacognition skills. Do you think their skill was specific to solving statistics problems or just problems in general?
That is a difficult question. I did not necessarily keep track of their problem solving in other scenarios. My guess would be because of their extended experience in STEM fields, they do have more problem solving experience, and that has led them to be able to solve these problems with a better strategy. But again, that actually points to my theory of make them take a programming class beforehand, because that gives them, they have to think about that. They have to work on problem solving, and that can be very, very helpful in scenarios like this one. That was a great question, whoever asked that one.
Thank you, Laura. All right, well, thank you, Vicki, for sharing your research with us today, and thank you all for attending. I don't yet know what our fall slate of webinars will look like, but I'm sure we'll have some good ones. I encourage you to keep your eye on your email or on the CauseWeb website. And also, please feel free to contact Vicki with other questions you have after this. So again, thanks everyone for attending, and hope to see you next time.
Thank you very much.